and driving to USC and then driving back, it would take lots of time. So I thought it might be easier to give a virtual talk. So it's a joint project with Roman Vershynin, who is from UCI, and Xinyuan, who is my graduate student here. It's about Jackson's inequality on the hypercube. So I will these slides I prepared actually for a colloquium talk at another places. So if you see that things are too simple, I apologize. It's more for wide audience rather than for some more focused group. Okay, let me see. What do we have? Hamming cube, it's of dimension n. These are strings of zeros and ones, vectors of length n. Each coordinate xi takes two values, 0 or 1. And the main problem I want to discuss is I give you any function on the hypercube of dimension n. They will be real valued most of the time. And what can we say about this approximation error? So what we do, we take f, subtract g. G is a polynomial of degree at most d. I will say what is degree. It's also a function on the hypercube. But it's a polynomial of degree at most d. And then you take maximum overall x's, overall zeros and ones, and then you look at the infimum of this difference. What can you say about this error? How small it can be if I give you some arbitrary function f, or if I give you some conditions on f? And what is the degree of a function on the hypercube? Degree is the minimal degree of a polynomial p from Rn to R such that p coincides with g on the hypercube. You know, you can, without loss of generality, you can think that p is a multilinear polynomial. It is linear in each variable, and minimal degree, and as soon as you restrict it on the hypercube, its degree is less or equal to n. So d is always less or equal to n. When d equals 0, we are talking about constants. You just subtract the constant. Yeah, right. That's the question. So how small this can be? And let me give you some quick examples about degree and about this smallness of this error of polynomial approximation. So if you take, for example, this function, minus 1 to the power x1 plus xn, then you can write it as a multilinear polynomial. Minus 1 to the power x1, it's just 1 minus 2x1, and then you have a product. It has degree n. It's a very high degree polynomial. And if for some d you manage to show that this error is strictly less than 1, notice that this function takes two values, plus 1 or minus 1. We will be calling such functions Boolean functions, or any functions which will be taking only two values will be called Boolean functions. And if you just subtract 0, which is just a constant 0, then this infimum is identically 1. But the question is, can you subtract some polynomial of degree d, which would make it slightly less than 1? And it turns out that as soon as you make it slightly less than 1, then necessarily degree of g must be n. This is not difficult to see, but this example shows that in general, if you want to get some non-trivial approximation, sometimes, it very much depends on the function. Sometimes you just need to choose the highest degree, which is n. So we will be putting some assumptions on functions. So you want to put some assumptions on functions to get some non-trivial approximation. And before I move, let me say a few words about degree. In general, finding degree of a function it's not absolutely a trivial problem. And knowing degree of the function, it has some applications in theoretical computer science. For example, there is a folklore statement that if you have a quantum algorithm which computes f exactly on each input, then the number of queries this algorithm makes is at least degree over 2. So knowing the degree of the function, we can get some information about the minimal number of queries quantum algorithm makes to compute f exactly. Also, there are already some other open questions, which is very trivial to formulate about finding degree. That if you have symmetric Boolean function, non-constant symmetric. Symmetric means that it does not depend on x1, x2, on the permutations of xi. And you know that it's a non-constant function, and you know it's Boolean, meaning that it takes only two values. Can you show that degree is at least n minus 3? This is a long-standing open problem, but easy to formulate. Okay, let's go to the next slide. So I want to start from a famous theorem, which was proved recently by Hao Huang, who resolved this sensitivity conjecture. It's a wonderful work published in Annals of Mathematics. He showed that his theorem in an equivalent way can be stated as an approximation problem. The result that he proved is equivalent to the fact that there exist some constants C1 and C2, universal constants greater than 0, such that for any Boolean function, we have the following bound on this approximation. It's less or equal C1 divided by d to the C2 and times L infinity norm of the sensitivity. Now, what is sensitivity of a function on the hypercube? It's a following object. You take at point x, you take f of x, and then you subtract f of xj. Xj, it is the same vector as x, but on jth coordinate, you just flip the bit. On jth place, you flip the bit. You subtract, you take the absolute value, so you consider differences in all n directions. You take absolute values of these differences, and then you sum up over all n directions. So this is a sensitivity at point x. And if you take the maximum overall x on the hypercube, so you look at the maximum sensitivity, then there is this, his theorem, Huang's theorem is equivalent to this statement that you can bound in terms of sensitivity, and there is a degree in the denominator. So if sensitivity is small, degree is large, then this is a small, the right-hand side is a small. Okay, bounding through sensitivity, it's a good starting point. And I was always interested in the question if such a statement holds for any real valued function, not just Boolean. Boolean, as I said, meaning that the function takes only two values, let's say 0 and 1. What about any real valued function? Okay, and here we have some results in the literature. The first result, it goes to Wagner in 1997, which says that if you just take approximation by constants, so these 0-degree polynomials, then this is bounded just by sensitivity, which is, well, in the previous slide, I had 1 over d. Usually we think that d is large. When d is 0, you should think 1 over d plus 1. You should think as a constant, so constant times sensitivity. So this is known for any real valued function if you just try to approximate with a constant. There is another result that we obtained recently with Vershynin and my student Xie, is that there exists a universal constant such that for any symmetric function, f, as I said before, symmetric means that the function does not depend if you permute coordinates x1, x2, xn. It really depends on the Hamming weight of the, it depends on the Hamming weight sum of the xi's of this vector x. Then there is this bound that c divided by d times, again, L infinity norm of sensitivity, exactly as in Huang's theorem, except we have slightly better constant. There is d just 1 over d, and this dk 1 over d is sharp. So having these two results, it seemed very possible that the statement actually holds for real valued functions. Okay, we have Boolean, we have case d equals 0, we have symmetric functions. Okay, maybe it holds for all functions. And this question was circulating around. I was thinking about this. I was also asking some of my colleagues, some other my colleagues were asking me. And we're very curious if one can prove such a statement for any real valued function, at least with some decay, or putting some constant which depends on d and goes to 0 as d goes to infinity. So if you try to approximate with large degree polynomials, you should expect that the error should go to 0. And before I move to the other results, I want to say that there are similar questions. There is absolutely no reason to talk about maximum norm. We can talk about LP norm. And for LP norm, there is this, LP norm, you take a uniformly distributed random vector on the hypercube. And the way you compute LP norm is just you take expectation of pth power of this thing at point X, and then you take 1 over p just in the normalized uniform probability measure on the hypercube. And there is a conjecture of Mendel-Naur, which is a very old conjecture, one of my favorite problems in this field. If you give me any power p between 1 and infinity, there exists a constant Cp greater than 0, such that this infimum overall polynomials of degree at most d is bounded like this. There is Cp divided by d, and then there is a Laplacian. So in the previous slide, I had sensitivity, but they are very closely connected to each other. Laplacian is the same thing as sensitivity, except I did not put absolute value here. Of course, Laplacian is less than sensitivity at point X, because if you put absolute value by triangle inequality, you put absolute values inside. Delta f of x in absolute value is less than s f of x. And for Boolean functions, they are just equal. For Boolean functions, absolute value of Laplacian at point X equals sensitivity at point X. So the previous results I could also formulate it for Boolean function in terms of Laplacian. There is no loss of generality, but I decided to write sensitivity because this was sensitivity conjecture, not Laplacian conjecture. Okay. And there are partial results. This is a major open problem. It has some nice applications in studying expander graphs. And there are some partial results. One says that, okay, we cannot put d, but we can put d to the alpha p, where you should think that alpha p is some number which is between 0 and 1. And when alpha p equals 1/2, when p is between 1 and 2, this is the famous result due to Mayer from 1984. Alpha p has some mysterious formula here coming from complex hypercontractivity, this angle that there is holomorphic calculus. Alpha p is this is less than 1 and greater than 0 when p is between 1 infinity minus this interval. This was due to myself and Alexandros Eskenazis. I think it was 2019. And there was this little gap to fill out when p belongs to this interval. This is also due to myself and Nazarov in 2020. This was consequence of solving complex hypercontractivity conjecture on the hypercube, or what was known Weisler's conjecture. Well, anyway, for p, there are some partial results. We don't have still correct decay d. D would be sharp if you would prove with d, but I don't know if this is correct. There are certain times in year when I think that this result with alpha p is sharp, but sometimes I think that it should be d. There are analogous questions on the Gaussian space with Gaussian measure, exactly the same problem. Laplacian is replaced by the Ornstein-Ulrich semigroup. And there are something is known in dimension 1. This is known, and this goes to some old results due to Freud in weighted approximation theory. And in one dimension on the real line, equipped with standard Gaussian, this is true. In higher dimensions, this is not known. But if you would solve this problem on the hypercube, then by central limit theorem and standard techniques, you would be able to obtain the result in the Gauss space in all dimensions. But this would be a little bit surprising because in approximation theory is not well developed. Techniques, tools are not well developed in higher dimensions. They are very much one-dimensional. Whatever tools they have, mostly they are one-dimensional. And it would be, I think, my major breakthrough in approximation theory for LP approximation by polynomials in weighted case in higher dimensions. Okay. Here is another, yes, and here is the result. I think one of the main results I want to present that is that which is very surprising because I was hoping about the opposite inequality. There exists a constant c such that for any n greater or equal to 1, there exists a non-constant function satisfying what? That if you take infimum overall polynomials and you approximate by degree very, very close to n, we are not even talking about d being fixed smaller than n, almost half of n, then this difference is greater, this universal constant. You can think about this universal constant as 1 over 10 times sensitivity. You know, in the previous slides, what I was expecting is that maybe there is a chance to have here less or equal and times 1 over d, or 1 over d to the sum power. As I showed you for Boolean functions, this was true. For symmetric functions, this was true. D equals 0, this was true. Maybe it is true in general, but it turns out that the answer is negative. There is a counterexample showing that even if you take polynomials of very, very high degree, you cannot approximate well enough with respect to the uniform norm. It will be separated by c, which is not going to 0. So there is this result. And the proof that we found, it shows that it actually holds if these polynomials of degree, of this funny degree, you know, this 0.4999, it's not something very special. It's a number which is of type, which is strictly less than n over 2, but it cannot approach to n over 2. It should be some c times n, where c is less than 1/2. So you can put any constant which is less than 1/2. That, yeah, the proof shows that if you take polynomials, this space of polynomials can be replaced by any subspace of dimension of this number. For example, why this number? Because the polynomials of this the space of these polynomials has this dimension exactly, right? Because there are constant terms, there are monomials xi, which is n choose 1, plus there are monomials xi xj, n choose 2, monomials xi xj xk, n choose 3, etc. So if you sum up to k from 0 to this, you get exactly the dimension of this space. But the proof of the theorem says that this is also true if you give me any subspace. Space, I mean, let's take L2 on the hypercube equipped with the uniform measure, and you take any subspace of this L2, then as long as it has dimension less or equal to this, I can always find a function which satisfies this inequality, which is not well approximated. So the polynomials has nothing to do, it turns out, in this counterexample. And the question I want to ask, okay, there is a typo. What about when degree is greater than 0.5 times n? Okay, we have a negative answer, but what about, it should be greater, less or equal, it's a mistake. What about when degree is greater than 0.4? Let's say degree is 0.9 times n. Can we have inequality with something going to 0? A proof breaks down. You cannot extend proof for larger degree. This is kind of largest, one of largest you can put. Is there a question?
I didn't hear it.
Okay, I cannot hear the question, so I guess I will continue. There exists a subspace, right? So is n over 2 sharp threshold? Is it true that if I have degrees larger, we don't know. We don't know. When degree is greater, we don't know. This is an open problem. But we know something else. We know that if you give, there exists a subspace of half of the dimension, such that this inequality holds true, that there is even bound 1 over n. And half dimension, because, you know, if you look just degree less or equal 0.5 n, then the dimension of the space of these polynomials is exactly half, meaning 2 to the n minus 1, right? So if you sum up k from 0 to n over 2, it will be 2 to the n minus 1. So half dimension, if we are talking about just subspace approximation. For subspace approximation, n over 2 is a sharp threshold. As long as subspace has a dimension less than n over 2, then you cannot approximate. As long as it has n over 2, then there exists a subspace which gives you always a good approximation. Okay, but for polynomials of dimension greater than the half, I mean greater than degrees greater than over 2, this is an open problem. Still, we don't know. But we have some partial results I will show you. But before I move to these partial results about approximation by high degree polynomials, I want to say that there is something in the literature which also was hinting about n over 2, that at least 50% of the Boolean functions cannot be approximated with degree n over 2, at least 50%, greater or equal to 1. As I said, if you take g equals 0, then absolute value of f is 1. It's minus 1 valued. If you try to approximate, you don't approximate. There is always a point where the difference is greater or equal to 1. So for Boolean functions, n over 2 is a sharp threshold. And there is another result, also a theorem due to O'Donnell-Servadio from 2008, which says that for almost all Boolean functions, it's 100% times 1 minus 2 to the minus n. So this is a this is a number very, very close to 1. So it's close to 100%. Of Boolean functions satisfy
So that's just background noise. Sorry, maybe
okay, that's just background. Okay, I thought that there is yes, as soon as you add little bit n over 2 plus c, let's say some universal constant times square root of n log n, you immediately are able to approximate almost all Boolean functions pretty well, 1 over n to the power 10, so almost 100%. So for Boolean functions, n over 2 is a sharp threshold in approximating Boolean functions. There are also some open questions. I think if you can remove this log n, or if you can little bit beat this square root of n times log n, but I'm not going to talk about that because we don't have results in that direction. But what we have, going back to, okay, now we understand that we cannot approximate by low degree polynomials. What if we try to approximate by high degree polynomials when n is of order 0.9 times n, when degrees of order 0.9 times n? In general, there is one kind of straightforward way to get the upper bound, like this, that if you give me any polynomial p on the real line, one-dimensional polynomial of degree at most d, then this difference I can always bound by 3 times sensitivity, and then there is this expectation of x. X is a binomial random variable, but normalized. I mean, it's divided by n, so binomial divided by n. You get expectation x times absolute value of px divided by expectation of px. So there is this universal kind of inequality you can have for any polynomial p on the real line of degree d. And then the problem just becomes, can we optimize this right-hand side and make it small? How small can we make it? And we did this little bit. I'm not saying we got the sharpest bound, but there is one standard way to get bounds of this type. It says that, okay, I can bound it by, so let's delta be 1 minus d over n. Then, so if you take infimum, there is a freedom to take infimum over all polynomials of degree d of this now one-dimensional problem, except this probability random variable is little bit complicated. No, it's not like uniform random variable on interval 0, 1. And the bound is like this. It's minimum delta, maximum delta square n to the power minus 2 over 3. Now, if d is close to n, let's say d is 0.9 times n, then delta will be 0.1. So you're getting something, right? So if delta goes to 0, but d has to be very close to n. It should be maybe n minus square root of n of this order to get something going to 0. Something going to 0. And to get such a bound, there are some standard techniques. You look at orthogonal polynomials with respect to this probability measure on the real line. And then you take, I think, orthogonal polynomial of degree d over 2, and then you look at the smallest positive root. These are Kravchuk polynomials, and this is essentially small behavior of the smallest positive zero of degree d over 2 Kravchuk polynomial with respect to this orthogonal with respect to this random variable. So, but I'm not claiming that this is sharp. Maybe one can do better. This we don't know. Okay, let me show you a few applications. Approximate degree. I want to say that approximate degree, what is approximate? It's let d be the minimal number such that this difference is less than 1/3. Suppose you have, think for example that f is a Boolean function. If you can make this difference less than 1/3, and there are many possibilities, let's choose d smallest such that this is true. Smallest such d will be called approximate degree. There is absolutely no reason to put here 1/3. You can put any number strictly less than 1. But there is some convention in the literature, so let's keep it 1/3. Then Huang's theorem that I presented in the beginning in the equivalent form, the original formulation is that sensitivity is greater than the square root of degree of f. Sensitivity conjecture itself was if you could bound it from below by some degree of f to some power, not necessarily square root. Huang got sharpest bound. But even this was even open if you would put some, if you are allowed to put some arbitrary power and also arbitrary constant. And this theorem does not hold, first question you can ask, is Booleanity necessary? The answer is yes, and there is a very simple counterexample. -1 to the sum of xi's divided by n. This function takes value in the interval -1, 1. Its sensitivity is 2, very easy to compute. Degree is n, so it has constant sensitivity, large degree, and this fails. This inequality fails. And if you think about counterexample, what you did, you just added very large degree monomial, kind of polynomial, but divided by n. If I would put n to the power, let's say 10, this would also work, right? So you just scale it, you shrink it, make it as small, but keep degree very large. But if you try to relax this statement, okay, does this hold if I replace degree by approximate degree? Because approximate degree of this function is 0, right? You don't have to, absolute value is less than 1 over n, so it's 1 over 3, it's 1 over n. Approximate degree, and this was an interesting question, and our result counterexample shows that the answer is negative in this case too, that even if you relax with approximate degree, there exists a function taking value in interval 0, 1 with sensitivity less than 1 and approximate degree very high, let's say 0.499 times n, almost n over 2. So there is no this relaxed version of sensitivity true. And another application I want to mention, it goes to the works of Mendel-Naor. Any function on the hypercube, we can write as a multilinear polynomial. Okay, there is one line of Fourier analysis. You can write as some overall subsets as ws of x, where ws of x is this function, -1 to the sum of j in sxj. So these are called Walsh functions, and these are orthonormal functions with respect to the uniform probability measure on the hypercube, and this is Fourier-Walsh decomposition. If n was equal to 1, then it just means that you write f of x as a linear function, right? A plus b times x1. Of course, f takes two values, you can find a and b so that it matches, this linear function matches. If n is 2, then it means that you approximate with you express it in terms of multilinear polynomial of degree 2. And Mendel-Naor showed that the infimum of L1 norm of f divided by Laplacian of f, and if you would take infimum over not all functions, but functions which are representable like this, but so you sum up over sets of cardinality log n. So they live in a sense on high, you should think about W's as a frequency. They live on high frequency. So if you take, it's also called tail space. If you take functions in frequencies at least log n, then there is a then there is this state inequality that this ratio is separated by universal constant, which is greater than 0. And what our example shows that you can actually replace this log n with 0. No, essentially n over 2, which is, I think, not a bad improvement. That this is because this space is pretty large compared to this space. So here I'm taking it from a much smaller class of functions, living on very high frequencies, and then there is still a statement that this ratio is greater than C. Okay, I would say that in their application, they were actually interested with, I think, n over 10. If there was a counterexample with n over 10, and they did log n. And actually, there is a counterexample. Okay. Okay. Now, I have some time, and maybe I will say a few words about proofs, unless there is any question in the audience. So let me illustrate the proof of this bound, this universal bound. And if somebody, now I replaced here x, I had binomial divided by n, I put n here, and because there was x, right? So I renormalized back, so x is just a binomial distribution. Just a binomial distribution. Okay, let me show you this bound. How do you get it? And then again, there is this question if one can bound this this ratio. So assume, let's pick a polynomial. And let's, without loss of generality, we can assume that the expectation of px is 1. We can divide polynomial by a constant. Now let's consider the following function, the hypercube h x1 xn. It's our polynomial, but at point x1 plus xn. This function h, if you take this polynomial of if you take this polynomial of degree d, when you open the parentheses, plug the sum, raise it to the powers, there will be xi's, cross product terms, there will be xi to the square, to the 3 power, but xi's take value plus minus 0, 1. So xi to the power k equals xi. So eventually you will end up with multilinear polynomial, which will be also of degree at most d. You will not gain degree if the original degree of p was at most d. And okay, this infimum is, what is it? Of course, it is bounded if I would pick very explicit approximant, very explicit polynomial for g. It will be the following. I take f of x, f of y, and I multiply by h, y, this is addition mod 2. So I have two vectors, y and x on the hypercube. I sum up coordinate-wise, and I take modulo 2. Sum, so xi plus yi modulo 2. So the output is 0 or 1. And then I take the average with respect to y. Y is the uniformly distributed variable on the hypercube, on this discrete cube, 0, 1 to the n. And this is some sort of convolution. And it's not difficult to show that this convolution has degree at most d, provided h has degree at most d. So I take it's a very natural candidate to try to approximate your function f with convolving and then figuring out what function h, what polynomial h I need to find, which would give me the best approximation. This is the way it is done on the real line, on the circle, on the torus. This is in these classical settings. And let's say that the maximum is attained at some point x star. So suppose it is attained x star. Then there is a little shifting. So let's introduce a new function. F of x will be f of x plus x star, addition modulo 2. And if you shift, you can notice that the maximum of the sensitivity does not change. So maximum sensitivity of capital F is the same as sensitivity of little f. But this shifting, what it does is that it just shifts things to the 0. So this difference will be equal f at 0 minus expectation over y of this thing, and of f of y plus x star, because I have here f of y. F of y equals this. But if you take expectation over this, you can change the variables and forget about x star, and then you can get here f0 minus average of f of y, h of y. I did not do anything complicated. This is just shifting and without loss of generality, assuming that the maximum is attained at zero. And you don't change the function sensitivity, it is the same. So we have this. Now I will use the simple triangle inequality and put the expectation outside. I can do that because expectation of h is 1. We assume that expectation of p with respect to the binomial random variable is 1. Okay, and how can we estimate this difference? So I will be focusing on estimating this difference, and later figuring out what is the best h I could choose. So far, we don't see sensitivity. You want to use somewhere that sensitivity, you know some information about the sensitivity of your function capital F. So now I wrote down the definition of the average. It is 1 over 2 to the n. And h, let me remind you that capital H is, this should be p, there is a typo. It is p of sum of y1 plus y2, etc., yn. And it's a symmetric function, right? When you take expectation, it only depends on the Hamming weight, of this function. Right, and then this equals this. And I will try to show this lemma that if we look at this difference, and then you sum up overall points on the hypercube 0, 1 of Hamming weight k, then there is a way to bound this sum as, let's say, 3 times sensitivity of f times this binomial coefficient. And if we prove this lemma, then you just replace this by this, and then it just easy to observe that whatever you end up, it will be exactly this that I was writing, expectation with respect to binomial distribution of x times absolute value of p of x, and we assume that expectation of p of x is 1, so you will end up exactly with what we are trying to prove. Okay, and there is one nice way to prove this inequality. So assume that the maximum sensitivity is 1. And we will consider the case when k is less or equal to n over 2. In the case it's greater than n over 2, there is one little trick. So we have that this sum overall points on the hypercube of Hamming weight k, we can bound by, so what we have here is, so I have a point 0 and I have a point y. I will be doing the following. I will be joining this point 0 and point y with some monotone path inside this hypercube. Monotone meaning that every time I will be going up, but I will not be going down. So I'll be joined by paths. There are many paths joining 0 with point y, and I will write it as a telescoping sum. That difference between 0 and y I can write as difference. I can write as the sum of differences of along these paths. And then I will just use the triangle inequality. And so suppose there is one path. I go up, I go left. So f0 minus fy is that f0 minus f, I went by one step up, and then plus f1 minus fy, that I went to the one step to the right. So you just write the triangle inequality, and then these paths, then you estimate by the differences with respect to the edges of this path. And you can write that this is less or equal 1 over k factorial, sum over y equals k in Hamming weight, and you sum up overall paths, joining points a0, a1, ak, and the sum goes over all monotone paths. A0 is the starting point, ak is the end point, And monotone, by monotone, I mean that, and the difference between A0, A1, you know, they differ in 1 bit. That's what it says. So, and monotone means that the paths, they will be only going up. That's what it says, that if you look at points, coordinates of point aj plus 1, they will be at least coordinates of point aj. Kth coordinate will be at least kth coordinate. So you will be only adding the bits 1. You will not be subtracting. So there is the simple observation. Now, I claim that these differences overall monotone paths, and then you sum up overall y's of fixed Hamming weight k, and then you normalize by k factorial. I can just rewrite, there is identity. I can rewrite as the sum overall points, again, on the hypercube of Hamming weight at most k minus 1 of what? Sensitivity of f times x, this Laplacian with absolute values, and then times certain numbers, which only depend on the Hamming weight of x and nothing else. And there is explicit formula you can get for these numbers. You know, it's a big sum of these differences with respect to these edges. You just pick an edge, and then you see how many times you count this edge on the left-hand side, difference along this edge. And here you can also see how many times you count difference with respect to that edge on the right-hand side. And then you just say that these two things should be equal, and you compute this constant. So what constants you should put so that this number of times the difference along a certain edge appears on the right-hand side equals number of times the difference with respect to that certain edge appears on the left-hand side. And there is this interesting number that shows up. These are not non-negative necessarily. They can be, I think they can be negative. Then there is this another technical remark that, okay, we put absolute values. So after that, we just put absolute values on the right-hand side. We put absolute values on px. And then let's assume that S of f is 1, maximum sensitivity. So right, and then you just need to show this inequality, that because when you sum up over some Hamming weights of weight L, it will be exactly n choose L, and then you want to show that this is bounded by this binomial coefficient to prove the previous lemma. And this inequality, unfortunately, only holds when k is less or equal to n over 2. It doesn't matter that I put 2 here. You could put 100, but it's not about this constant. It just does not hold for large n's. When k is close to n, it just fails. Okay, and there is a trick to cover the opposite case. Okay, now this I kind of gave you general idea how you prove when k is less or equal to n over 2. And when k is greater than n over 2, you do the following. You use Wagner's result. Wagner says that infimum of f of x minus c, and you take c with overall constants, this L infinity norm is bounded from above by sensitivity. This is the equals 0 case of the statements we are trying to prove. And no, but he actually proved a little bit more than that, that if you look at the difference between f0 and f1, if you look at the difference at the corners of the hypercube, it is bounded by maximum sensitivity. And right, and then what you do is that in the previous slide, we've been trying to estimate f0 minus f1, right? Then you just add f1, subtract f1, use triangle inequality, f0 minus f1, you estimate by this. Then you end up with sum up of constants 1 of Hamming weight k, so you end up with this binomial coefficient. And then you kind of flip the problem Now you don't approximate f0 minus fy, but you approximate f1 minus fy. So there is this little small argument, and now you are again back to the previous problem, because distances between y and 1 will be less than n over 2 Hamming weight distances between y and the corner 1, 1, 1. And then you do the same thing, and then you, in that case, you know that the statement is true, and then you prove this result. Okay, I think I still have okay, I don't know if I should finish at 45 or 50, but I think I will stop here. So I have. Thank you very much.
Thanks a lot. Yeah, I guess you could add 2 more minutes, but yeah, we can do questions instead. Anybody online or in person have any questions?
It seems to me that the kind of the clever thing is to express things in terms of these upright paths. And do you think that there's anything to be gained by optimizing that step in any way? Because you are looking at basically some sort of average over all possible paths, right?
Yes,
That's where the k-factorial is.
right. Maybe you can find some probability measure, better measure on this path. We took uniform, right? So no, I don't know. I tried to optimize, but I could not. We tried to optimize, but we could not get. We suspect that this this step might be sharp, but we don't have explanation of it. Right. Yes, it's a good question, but I just don't see how to better optimize it. Maybe there is a better choice of paths.
Well, what about the bounds in terms of the binomial coefficients that you had, like one of the lemmas in the last two?
No, this is fine. This I don't care about these constants. Maybe one can improve in this argument, this number 3, where this number 3 one can improve. It's about this constant, this binomial.
No. Can you go 2 slides forward? Okay, one more. Okay, one more. That's the statement.
Yes.
Like here you have some sort of a lemma, right? Do you know if this lemma is sharp in any reasonable way?
Well, when y equals 1, this is sharp. When k for, I think this is sharp. Yes, no, I think this is sharp. The only place I think I'm losing, it could be that when I apply triangle inequality here, when I take out this expectation outside and put the absolute value inside, I think that we might be losing here. If the statement is not sharp, we might be losing here. That's one place I'm mostly suspecting where we could be losing. Another place I'm also suspecting where we could be losing, that I started approximating by convolution.
Right?
Yeah, I think this may not be true anymore, at least from my experience working in LP approximation on the hypercube. At least there we are convinced that the convolution approximation is not the best one. There should be another thing.